Welcome back to the Mechanics of Solids lecture series. In this series of videos, we're solving examples considering buckling in axial loaded members. As we discussed in class, sometimes we want to design an axial loaded member for an allowable stress, considering the possibility of both buckling or yield. This example will illustrate that concept. We're going to consider a pin-pin column with an 8-inch by 8-inch square cross-section. Draw a picture of the cross-section, 8 inches by 8 inches. The material is aluminum with an elastic modulus of 10,000 ksi and assumed yield stress of 50 ksi. We're asked to find the allowable stress, skipping down to the second part, the allowable stress for a 6-foot long column and a 15-foot long column. So sigma allowable for L equals 6 feet and L equals 15 feet. And we're asked to assume a factor of safety equals 2 against both yield and buckling, whichever may control. In order to have a better understanding of what's going on and how the length affects the consideration of both yield versus buckling, we'll plot an overall stress limit versus slenderness ratio. That would be sigma versus L over R. And we'll interpret the answer to the second part in the context of this sketch. Okay, so to start with, notice I want to plot sigma versus L over R, L being the length, which in this case can vary, and R being the radius of gyration. R equals square root of I over A. So R is a fixed property of the cross-section and doesn't vary once we determine the cross-section properties. So we'll go ahead and compute R. I for the square section, BH cubed over 12, same in both directions, so that would be 8 inches times 8 inches cubed over 12, which computes to 341.3 inches to the fourth. A is equal to just B times H, or 8 inches squared, which is 64 inches squared. So therefore, our R computes to the square root of 341.3 inches to the fourth divided by 64 inches to the inches squared, and that is about 2.3, and the units are inches. Okay, so that's the slenderness ratio. Now, we also developed, based on the critical buckling load, that the critical buckling stress can be written as sigma crit equals pi squared E divided by L over R squared. Okay? And a stress limit versus slenderness ratio, we sketch out what it looks like. Sigma versus L over R. Okay? This sigma critical is inversely proportional to L over R squared. So it's going to be like a quadratically decreasing curve like this. Okay? And it would extend all the way up, but what happens for small slenderness ratio, the yield stress controls rather than the buckling stress. So the curve would come straight across like this, where this flat portion would be determined by sigma y, which in this case is 50 ksi. Okay, so the next thing I want to find is the value of L over R that determines the transition from a yield-controlled member to a buckling-controlled member. And the more slender members are going to be controlled by buckling. In order to do that, we want to set sigma crit equal to sigma y, which is that will be true at that transition point, and solve for L over R. So L over R squared, I can say, equals pi squared E divided by sigma y, and L over R equals the square root of that quantity. And we'll go ahead and put in the numbers now. Pi squared times E, which is 10,000 ksi, divided by my sigma y, which was 50 ksi, and that computes to about 44.4. And notice this is a dimensionless quantity, the length, which is a length, and radius of gyration, which is a length. Okay, so my transition point here is 44.4. To have a little bit better understanding of this curve, I'm going to compute a few more values on the buckling controlled portion or downward sloping portion. Let's start a new screen for that. I've summarized what we already know. Okay, let me compute the critical buckling load for L over R equals 60. Sigma crit in that case, pi squared times 10,000 KSI divided by 60 squared, and that would be equal to 27.4 KSI. So locate that point on the curve somewhere over here, about 60, and the value is 27.4. Okay, and let me also compute maybe for an L over R equals 80. Sigma crit equals pi squared times 10,000 KSI divided by 80 squared. And that computes to about 15.4 KSI. So I'm going to come over here to about 80 and locate that point on my curve, 15.4 KSI. These are all KSI, and so on. So we get the idea of the trend. Okay? Now let's turn to the second part of our problem and find the allowable stress if the column is 6 feet long and the allowable stress if the column is 15 feet long. Okay? Key here, we want to find the slenderness ratio, compute sigma crit, sigma y, and see which one controls. So start with L equals 6 feet. Okay, the L over R ratio there, L over R equals 6 times 12 inches. So we want to compute in inches, divided by R, which we computed as 2.3 inches. That value is about 31.3. So by inspection of our curve, we note that 31.3 is less than the transition value. The point is somewhere over here. So this is a yield controlled member. So sigma allowable in that case is going to be sigma y divided by the factor of safety, or 25 KSI, for L equals 6 feet. 6 feet. Okay? That's the first part. If L equals 15 feet, I think you can see maybe what's going to happen here. The L over R ratio, 15 times 12 inches divided by 2.3 inches, that computes to a much larger number, which is 78.3. And we can see by looking at sigma versus slenderness ratio that this is greater than the transition value. In fact, it's very close to this point that we computed here, and it's going to be a buckling controlled member. So we'll compute sigma crit for that case, pi squared times 10,000 KSI divided by the slenderness ratio, 78.3 squared. And for that one, we get a 16.1 KSI for L equals 15 feet. So that's our answer to the second part. And that makes sense if we look at our sigma versus L over R, stress limit versus slenderness ratio. That point would be about right here, just a little bit larger than 15.4. So that answer makes sense. So to summarize, a 6-foot column is a yield-controlled member and would have an allowable stress equal to sigma y over the factor of safety. The 15-foot column is much more slender and therefore is a buckling controlled member. Will have allowable stress equal to sigma crit divided by 2. Oh, I forgot to compute that. Sigma allowable equals sigma crit divided by 2, which is going to be about 8.05 KSI. Okay, and that concludes this example.